Welcome to AP Statistics. Today, we are exploring one of the most practical and powerful tools in data analysis. Topic 4.3, Justifying a claim based on a confidence interval for a population mean. Our learning objectives for today are as follows. First, interpret a confidence interval in context. Second, justify claims using intervals. And third, understand relationships between sample size, confidence level, and interval width. By the end of this lesson, you will be able to explain exactly what a confidence interval tells us about a population, how to use it to evaluate real-world claims, and how changing your sample size or confidence level impacts your results. Let's start with the definition. A confidence interval, often abbreviated as CI, is an interval of plausible values for a population parameter. In statistics, we rarely know the true population mean, which we call mu. We use a sample mean, x bar, to estimate it. But because of sampling variability, we know x bar isn't perfect. A confidence interval gives us a range of values where the true mean is likely to hide. Before we look at the numbers, we must understand what it means to be confident. This is a common area for misconceptions on the AP exam. The interval may or may not contain the true population mean. Think of a confidence interval like a net being thrown at a target. The target is the true population mean, mu. The net is our interval. Because the interval is calculated from a random sample, it's subject to the luck of the draw. Sometimes our sample is representative, and our net captures the mean. Other times, by chance, our sample is an outlier, and our interval misses the mean entirely. This is the long-run interpretation. In repeated random sampling, approximately C% of intervals created will capture the population mean. If we were to take thousands of samples of the same size and build a 95% confidence interval for each one, about 95% of those intervals would successfully contain the true population mean. We don't know if our specific interval is one of the winners, but we trust the process that produced it. When you are asked to interpret a confidence interval on the AP exam, there is a specific phrasing you should use to ensure you cover all the requirements. We are C% confident that the interval from lower to upper captures the true population mean of context. Let's try an example. Suppose a researcher wants to estimate the average amount of sleep high school students get per night. Based on a random sample, they calculate a 95% confidence interval of 6.2 to 7.4 hours. Notice how we include three things: the confidence level, the interval values, and the context, which is the average sleep for all high school students. Notice what we don't say. We don't say, there is a 95% probability that the mean is in this interval. Once the interval is calculated, the mean is either in it or it isn't. The 95% refers to our level of confidence in the method we used. Include the parameter, that is the population mean, in your interpretation, not the sample mean. We already know the sample mean is in the interval. It's usually right in the middle. We are trying to make a statement about the entire population. Confidence intervals are not just for estimating, they are powerful tools for making decisions and justifying claims. This is a core skill for topic 4.3. An interval provides evidence to support or refute a claim about a population mean. The logic is simple. If a claimed value falls inside our confidence interval, that value is a plausible value for the population mean. If the claimed value falls outside the interval, we have convincing evidence that the claim is likely incorrect. Let's visualize this with a number line showing a confidence interval from 10 to 15. Notice that 12 is inside the interval, so it is a plausible value. However, 18 is outside the interval, making it not plausible. Imagine a company claims that their light bulbs last an average of 1,000 hours. A consumer group constructs a 99% confidence interval for the true mean lifespan. The resulting interval is 920 to 980 hours. Take a look at that interval. Does it contain the 1,000 hours the company claimed? No, it doesn't. Since 1,000 is not in the interval, we have convincing evidence that the true mean lifespan is less than 1,000 hours. Because the entire interval is below 1,000, we can specifically justify the claim that the bulbs last less than advertised. This is how you use an interval to test a claim without a formal significance test. Now let's talk about the anatomy of a confidence interval and how its size changes. This is vital for understanding how much precision we have in our estimate. The general formula is the point estimate plus or minus the critical value times the standard error. The point estimate is our sample mean, x bar. The part we add and subtract is called the margin of error. The margin of error, or ME, equals t star times the sample standard deviation over the square root of n. The margin of error determines the width of the interval. There are two main ways to change the width. changing the confidence level, and changing the sample size. First, consider increasing the confidence level. This causes the critical value, T star, to increase. Consequently, the margin of error and the width of the interval also increase. Think about it logically. If you want to be more certain that you catch a fish, do you want a smaller net or a larger net? To be more confident, you need a wider interval to account for more possibilities. This means as the confidence level goes up, the T-star critical value gets larger, making the whole margin of error grow. You gain confidence, but you lose precision. Now let's look at increasing the sample size. Increasing n decreases the standard error, which in turn decreases the width. When we have a larger sample size, n, we are dividing by a larger number in our formula. This makes the standard error smaller. Larger samples provide more consistent data, which allows us to be more precise. So, increasing the sample size makes the interval narrower, without having to sacrifice your confidence level. Here is a useful rule of thumb. The width is proportional to 1 over the square root of n. This means if you want to cut your interval width in half, you actually need to quadruple your sample size, because the square root of 4 is 2. Now that we have covered the theory, let's work through a detailed example involving the difference between two population means. This is a common scenario in AP statistics, where we compare two groups. Suppose a farmer wants to know if a new organic fertilizer results in a different average growth than the standard conventional fertilizer. They take a random sample of 30 plants for each type. Our data shows an organic mean of 54 inches and a conventional mean of 50 inches. The calculated 95% confidence interval for the difference, mu1 minus mu2, is 1.5 to 6.5 inches. In this case, the parameter we are estimating is the population mean difference, which is mu1 minus mu2. Step 1. Interpret the interval. Based on our template, we are 95% confident that the interval from 1.5 to 6.5 inches captures the true difference in the mean height of corn plants grown with organic versus conventional fertilizer. Step 2. Justify a claim. The conventional fertilizer company claims there is no difference between the two fertilizers. Does this interval support their claim? If there were no difference, the value 0 would be a plausible value for the difference. Does the interval 1.5 to 6.5 contain 0? No, it doesn't. Since 0 is not in the interval, we have convincing evidence that there is a significant difference between the two fertilizers. Furthermore, because the entire interval is positive, we have evidence that the organic fertilizer results in a higher mean growth. Step 3. Consider changes. What if the farmer wanted a narrower interval? They could either decrease their confidence level to 90%, which would make the critical value smaller, or they could increase the sample size from 30 plants to, say, 100 plants. Increasing the sample size to 100 would decrease the standard error, giving a much more precise estimate of the benefit of the organic fertilizer. To ensure you are fully prepared for the AP exam, let's dive into another detailed scenario. This time we will look at how we justify a claim when the interval does contain the value in question, and how to interpret the results of a mean difference from a paired design. In this study, 10 office workers are timed on both a standard keyboard and a new ergonomic one. The researchers calculate the difference for each person, and then find the mean of those differences. The resulting 90% confidence interval for mu diff is negative 2.4 to 5.8 words per minute. Let's break this down. First, the interpretation. We are 90% confident that the interval from negative 2.4 to 5.8 words per minute captures the true mean difference in typing speeds for the population of office workers using these two keyboards. Now, for the justification. A consultant claims that the ergonomic keyboard increases typing speed. Do we have convincing evidence for this? If the new keyboard is faster, we would expect the mean difference to be positive. While our interval includes positive values like 5.0, it also includes negative values like negative 2.0, and it includes 0. Since 0 is contained within the 90% confidence interval negative 2.4 to 5.8, we do not have convincing evidence that there is a difference in the mean typing speeds. A mean difference of 0 is a plausible value. Take a moment to think about this. Even though our sample mean might have been positive, in this case, the center of the interval is 1.7, the margin of error is large enough that we can't rule out the possibility that the keyboard actually makes no difference, or even makes people slower. When 0 is in the interval, we say the results are not statistically significant at that confidence level. This is a crucial distinction. We aren't saying the difference is 0. We are saying we don't have enough evidence to claim it isn't 0. Let's apply these concepts to a more complex real-world scenario to see how statisticians think through problems. Imagine an environmental agency is monitoring a river for a specific pollutant. The legal limit for this pollutant is 5 parts per million. The agency takes a random sample of 25 water specimens from various locations in the river. They use this data to construct a 98% confidence interval for the true mean level of the pollutant in the entire river. Let's evaluate this. First, interpret the interval. We are 98% confident that the interval from 5.2 to 6.4 parts per million captures the true mean concentration of the pollutant in this river. Now, we must justify whether the river is safe according to the law. Does this interval provide evidence that the river exceeds the legal limit? Yes. Since the entire interval 5.2 to 6.4 is strictly greater than 5.0, we have convincing evidence that the true mean pollutant level exceeds the legal limit. Notice that, because the lower bound of our interval is 5.2, even our most conservative estimate of the mean is still above the legal threshold of 5.0. What if the agency wanted to be more precise before taking legal action? They decide they want to reduce the margin of error by half. Recall our rule about sample size. The width is approximately proportional to 1 over the square root of n. To cut the width in half, we need to multiply the sample size by 4. By taking 100 specimens instead of 25, the agency can create a much narrower interval. This gives them more precision, which is essential when lives or legal consequences are on the line. With the larger sample, the interval shrinks around the sample mean. If the new interval is 5.5 to 6.1, we are still confident the limit is exceeded, but our range of plausible values is much tighter. Now, let's explore a very common trick question on the AP exam that tests your understanding of the relationship between the confidence level and the width of the interval. Suppose we have a fixed set of data from a study on the average weight of a specific breed of dogs. Using this data, a student calculates both a 95% confidence interval and a 99% confidence interval, without being told which is which. Can you identify which interval belongs to which confidence level? Recall that to be more confident that we have captured the true mean, we need to provide a wider range of plausible values. Looking at our numbers, interval B is wider. It stretches further in both directions than interval A. Therefore, interval B must be the 99% confidence interval, and interval A must be the 95% confidence interval. This is because the critical value, T star, for 99% confidence is larger than the T star for 95%. Here is the relationship recap. As the confidence level goes up, the critical value T star goes up, the margin of error goes up, and the width of the interval goes up. It is a trade-off. If you want more certainty, you have to accept less precision. If you want a more precise estimate, a narrow interval, you have to accept a lower level of confidence unless you can increase your sample size. When one goes up, the other tends to go down. The only free lunch in statistics is increasing the sample size, which allows you to improve precision without losing confidence. Let's take all the concepts we have discussed, interpretation, justification, and the relationships between variables, and put them into one final comprehensive example. This reflects the depth you might encounter in a free response question on the AP exam. A tech reviewer compares the battery life of phone X and phone Y. They sample 40 of each. The parameter of interest is mu sub X minus mu sub Y, the mean difference in battery life hours. The reviewer constructs a 95% confidence interval for the difference in mean battery life between the two phones. First, we need to interpret this interval in the context of the study. We are 95% confident that the interval from 1.2 to 3.8 hours captures the true difference in the mean battery life for all phone X units versus all phone Y units. Next, let's use this interval to justify a claim. The manufacturer of phone X claims that their phone lasts, on average, at least 5 hours longer than phone Y. Does our interval support this claim? Look at the interval, 1.2 to 3.8. Every value in this interval is less than 5. No, the interval does not support the claim. Since the entire interval, 1.2 to 3.8, is below 5.0, we have convincing evidence that the true mean difference is actually less than 5 hours. Now, what if the reviewer wanted to report the results with 99% confidence instead? How would the interval change? If we increase the confidence level from 95 to 99, we need a larger critical value. This will increase the margin of error, making the interval wider. The interval would expand. It might look something like 0.8 to 4.2. We would be more confident in our capture, but our estimate of the exact difference becomes less precise. Finally, what would happen if the reviewer had only tested 5 phones of each type instead of 40? A smaller sample size increases the standard error. This makes the margin of error larger and the interval much wider. With only 5 phones, the interval might have been so wide that it included 0, meaning we couldn't even prove which phone was better. By understanding these dynamics, you can better design experiments and more accurately critique the statistical claims you see in the world. As we wrap up our look at topic 4.3, let's summarize the key takeaways. Understanding how to navigate confidence intervals is not just about doing math, it's about making sense of uncertainty. First, interpretation. We say we are C% confident the interval contains the parameter. Second, justification. We check if a claimed value is inside or outside the interval. And third, relationships. We analyze how sample size and confidence level affect the width. Remember that the C% in a confidence level describes the success rate of the method. If you use a 95% confidence level, you are using a method that works 95% of the time in the long run. Let's review the key relationships. A higher confidence level leads to a wider interval. A larger sample size leads to a narrower interval. And remember, the margin of error equals the critical value times the standard error. When you are justifying a claim, always check if the hypothesized value, often 0 for differences, or a specific target for a single mean, is inside the interval. If it is not in the interval, you have convincing statistical evidence to reject that claim. On the AP exam, use this visual checklist. Did I state the confidence level? Did I include the interval values? And did I mention the population parameter in context? Confidence intervals are a bridge between sample data and population knowledge. By mastering these interpretations and the logic behind them, you are well on your way to thinking like a statistician and succeeding on the AP statistics exam. Before your next study session, try to find a news article that mentions a margin of error. Ask yourself, what would happen to that margin if they surveyed 4 times as many people? Take a moment to reflect on the trade-offs between precision and confidence. Being able to explain why an interval is wide or narrow is just as important as knowing how to calculate it. Thank you for joining me today, and keep practicing your interpretations.